In this video, we'll consider a system of first-order linear equations. x1 dot equals x1 plus x2, x2 dot equals 4x1 plus x2, and use techniques from linear algebra to find the general solution for x1 and x2. Okay, so let's begin by writing this as a matrix equation. So we can put x1 and x2 into a vector. So the left-hand side becomes a derivative of a vector. And then the first equation we can put into the first row of the matrix, x1 plus x2, with a matrix multiplying a column vector x1 and x2. And the second equation we can put into the second row, 4x1 plus x2. Okay? So this is a matrix equation. Symbolically, we can write this as the vector x dot is equal to the matrix A times the vector x. Okay? This is a system of first-order equations. Here A is the 2x2 matrix 1, 1, 4, 1. Okay. To solve this equation, we need an ansatz. Our ansatz will be our usual exponential ansatz, but in this case, it's as a vector. So we try x as a vector, which is a function of time, equal to a vector which is independent of time, v, times our exponential function e to the lambda t. Okay. Now when we substitute in this ansatz, the derivative of x, because v is independent of time, will just bring down a factor of lambda. So substitution into our ansatz gives us lambda v times e to the lambda t equals a times v times e to the lambda t. And we see that the e to the lambda t cancels. So it becomes a linear algebra equation of the form a times v, the right-hand side, is equal to lambda v. And this is the well-known eigenvalue problem from linear algebra. Okay, so we've reduced the solution of the system of ODEs using our ansatz into a linear algebra eigenvalue problem. Okay. So how do we find the eigenvalues and the eigenvectors of this problem? The eigenvalues we find by looking at the determinant of A minus lambda I equals 0. That's our characteristic equation. A is 1, 1, 4, 1. So this becomes the determinant of A, 1 minus lambda on the diagonal, 1, 1 off diagonal, 4 off diagonal, 1 minus lambda on the lower diagonal. The determinant of this matrix equals 0, which we can expand. So that is lambda minus 1 squared from the diagonal term, minus 4 equals 0, so equal to 4. And then we can solve this by taking the square root. So we have lambda minus 1 equals plus or minus 2. And then we get lambda equal to 2 plus 1, 3, minus 2 plus 1, minus 1. So we have two roots of this characteristic equation, so we can put a subscript 1 and 2 on that. Okay? So now we have the eigenvalues, so we need to find the eigenvectors. So let me rewrite A here. That's our 1, 1, 4, 1. And then we have two eigenvalues. Lambda 1 is 3. Lambda 2 is minus 1. Okay? So let's find the eigenvectors then. We can compute the eigenvectors. We know v is an eigenvector, then AV equals lambda v. So the eigenvectors are found from the equation A minus lambda v, A minus lambda I, times the eigenvector v equal to 0. Such an equation will give us the eigenvectors. So we do solve this equation for each eigenvalue. So we start with lambda 1 equal to 1. A minus lambda 1, I, is, lambda 1 equal to 3. Lambda 1 equals 3. So A minus 3i gives us 1 minus 3 is minus 2. 1, 4. 1 minus 3 is minus 2. Times the eigenvector. So there's going to be two eigenvectors. So the first eigenvector I will put in the first column of an eigenvector matrix. So I'll call this components v row 1 column 1, v row 2 column 1. So that will be the components of v1. And that's supposed to be equal to 0. Okay? If you look at this, you'll see that the equation from the second row is just minus 2 times the equation of the first row. So we need only consider one row of this matrix. So we find that minus 2, the first component of v1, plus 1 times the second component of v1, v21, equals 0. So that v21 equals 2v11. Okay? So the first eigenvector associated with lambda 1 has top component v11, second component v21, which is 2v11, which we can write as v11, 1, 2. And v1, of course, is the eigenvector is determined only up to a constant. So we could, for simplicity, we can just choose v11 equal to 1. Okay, so that our first eigenvector will be 1, 2. Okay. Now we can find the second eigenvector. So the second eigenvector is lambda 2 equal to minus 1, right? A is 1, 1, 4, 1. So let me write that here. A is 1, 1, 4, 1. So we have the eigenvalue equation, eigenvector equation, A minus lambda I v equals 0, with lambda 2 equal to minus 1. So that means A plus I times v equals 0. We add 1 to the diagonal. So we get 2, 1, 4, 2 times the second eigenvector, which will be the first row, second column, second row, second column, equals 0. Again, the second equation, the equation from the second row is just a multiple of the equation from the first row, so we don't need to consider it. So this eigenvector will satisfy 2 times v12 equals plus v22 equals 0, or v22 equals minus 2 v12. So the second eigenvector, v2, is going to be equal to v12, and the v22 is minus 2 v12, which is v12 1 minus 2. So again, we can choose v12 equal to 1. So the second eigenvector becomes 1 minus 2. Okay, so putting it together, we found 2 eigenvectors, right? We found 2 eigenvalues, so lambda 1. The first eigenvalue we took to be 3, and then the first eigenvector we determined is 1, 2, and the second eigenvalue is minus 1, and the associated eigenvector was 1 minus 2. And remember, our ansatz was x equal to v times e to the lambda t, right? So we can use the principle of superposition to find the general solution. So we found 2 solutions, v1 e to the lambda 1t and v2 e to the lambda 2t, and now we can multiply each of them by a constant and add them together to get the general solution. So we found now the general solution, x of t equals c1 times v1 1 2 times e to the lambda 1t e to the 3t plus c2 times v2 1 minus 2 times e to the lambda 2t e to the minus t, and that's the general solution. Okay. In the remaining time, we can see how to sketch the phase space diagram. So that would be a sketch of x2 versus x1. To make this sketch, what we do is to draw the eigenvectors. So if C2 was equal to 0, right, initial conditions was such that C2 was equal to 0, then all the solutions would follow this first solution, which means that x2 would always be equal to 2x1. x2 would be 2x1. So if x2 is 2x1, that's a line which looks like this, positive slope. So this is x2 equals 2x1. And along this line, the solution is growing as e to the 3t. Okay. The second one is if c1 is equal to 0, then x2 is equal to minus 2x1, which is a line of negative slope. And there the solution is decaying to the origin. So by drawing the eigenvectors first, we can sketch then how the solution behaves, starting anywhere on this plot. So any initial condition, the solution will behave in somewhat like this fashion. Okay? So that means if we start here, then the solution will follow this curve.